Welcome back to another lesson for chemistry. And before we begin this new lesson, I want to focus your attention to the surveys that we've been providing every day. So every Monday, I will be posting a survey. Tuesdays, that belongs to Mr. Diaz. Today, which is Wednesday, Ms. Garcia will be posting her own survey. Thursday will be Ms. Torres. Friday, Mr. Cellier or myself. But we have been noticing that a lot of y'all are not turning these surveys in on time. And the reason why we need these surveys to be turned in by noon, it's because that gives us an idea of who's logging in and who is most likely working on their assignments. So, for example, today is Ms. Garcia's day to have a survey for you all. And it's on her teams, on her general channel on the posts. And she even made it an important post because it's such an important survey and we need this information before a certain time, okay? If we don't get that survey, then that just means that we're gonna have to go home. We're gonna have to make sure that if you're doing all right, if you are working on these assignments. We just really wanna know if you are up and doing these assignments, all right? I will also be sharing every survey that a teacher shares. So this is the same survey by Ms. Garcia that she has on her teams. If you already did it, then you don't have to do it again, okay? So this only has to be completed just once. It's not necessary that you have to do it for every single team's announcement that you make, but it is very important. And the reason why I also share these surveys from other teachers, it's because I really do want major outreach. So if you didn't see it in Ms. Garcia's, but you did see it in mine, well then that's good. We just want to reach out to many students as possible. We also want to make sure that you all are logging in into teams and actually working on your assignments. So that's pretty much the main purpose of these attendance surveys. We just want to make sure if you're logging in and most likely working on these assignments. Alright? Okay, so with that being said, let's move on to the lesson for today. And calorimetry. Last lesson, I do want to apologize for the editing skills that I don't have, and my cat being in the way as well. It wasn't a good day, and so I was trying to tackle the same concept that we learned on Thursday, which is very math intensive, but I wanted to show you how to do these examples by hand, which is why I took the liberty to record the whiteboard and the 3 examples that we saw on Thursday. Knowing how to do these math examples are very important, and they're basic algebra 1 skills. I will also be teaching a new lesson that is very math intensive, and I will also be approaching it differently, where I'm going to show you how to do these by hand rather than relying on a calculator. What you probably do need is a 4 basic function calculator, and those are the calculators found on your phone or any just boring cheap calculator that you find either at the dollar store or at Walmart. Okay, so label today's notes with this title, calorimetry. Calorimetry is actually a very useful concept in the food industry because we can actually figure out how much calories or energy certain food have. If we know the mass, if we know the change in temperature, etc., we can actually find the amount of calories. And so with this concept, we would have been doing an awesome lab experiment where we would have figured out the calorie amount of Cheetos or hot Cheetos by burning them. But unfortunately, due to the circumstances, then we can't do that. But it's still a very interesting concept, and it's very useful, especially in the food industry. Before we begin, I just want you to take a minute of this scenario. So you're dropping a very hot metallic ball in this very cold cup of water. What's going to happen? And so I'm going to give you a hint. The ball either gets hotter or the ball gets colder. Take a moment and determine what happens to the ball. So because I'm dropping the very hot ball in cold water, I think the ball will just get colder. the heat energy moves from the ball to the water, or the heat energy moves from the water to the ball. Take another moment, determine what happens. Remember that energy moves from high energy to low energy. The heat energy moves from hot objects to cold objects. We have seen that. Please remember that. In this scenario, that heat energy is going to move from the red hot ball to the cold water. And that's basically because heat is only able to move from hot to cold. This last scenario, the ball particle's kinetic energy decreases, or the water molecule's kinetic energy decreases. So take a moment, this one's a pretty complicated one. Remember that kinetic energy is directly related to the temperature of an object. If I increase the temperature of an object, then the kinetic energy also increases. So, because my ball is losing that heat, it's losing the temperature, that means that the kinetic energy of that ball will also decrease. So calorimetry, it has a basic definition. It's a technique that we can use to measure the amount of heat involved in a chemical or physical process, and that is known as calorimetry. It's used to measure the amount of heat transferred to or from a substance. So pause this video, make sure that you write these 2 bullet points down. In calorimetry, we use a calorimeter to measure the heat transfer. We're not very creative with names. And a calorimeter involves a container that holds in a liquid with a thermometer. Alright? In order for us to do these calorimetry problems, we have to understand the law of conservation of energy. The law of conservation of energy states that heat cannot be created or destroyed. In the last example that we saw, the one with the red hot ball and the cold cup of water, the heat is leaving the hot object, and that same heat that the ball is losing is the same amount of energy that is gained by the water. The heat was not lost. It was just transferred to the surroundings or the water. And we can express the law of conservation of energy by a very simple equation. That equation is the negative Q lost equals the Q gained. Remember back from that MCAT lesson, Q represents heat. In this scenario, or in this slide, this Q represents the same thing. Negative Q lost represents the amount of heat that was released by a hot object. This Q gained, this is the value of energy that was absorbed by the cold object. So in this case, if we had a value of energy lost by that red hot ball, it would go on the left hand side and it would have a negative sign. Think about it as an exothermic process. That red hot ball is releasing energy, so that's why it has that negative sign. The water, the amount of heat absorbed is the same amount of heat that was lost by that ball. And notice that it does not have a negative sign, so it's a positive because it's an endothermic process. So, like I said, you're going to have to remember the concept from Thursday, Q equals MCAT, where Q represents the amount of heat absorbed or released. M stands for the mass. The CP stands for the specific heat of a substance or an object, and delta T represents the amount of temperature change. So it's the difference between the final and the initial temperature of an object. Because I have two Q's on both sides of this equation, I'm going to rewrite this MCAT on both sides while conserving the negative sign. Just like this. And remember I said that the object that loses the heat is the hot object, just like we saw in that example. So if we substitute this Q into this negative Q, where I'm gonna fit MC and delta T on the left hand side, I need to make sure that I keep the negative value, okay? And the mass, the specific heat, and the change in temperature, it all belongs to the hot object. The object that gained that energy is the cold object, and so that's going to be the mass times the specific heat and the change in temperature of that cold object. And we're going to see a few examples and how we're going to use this equation. We can rewrite this equation because I know that delta T is the same thing as the final temperature minus the initial temperature. So it just gets a little bit more complicated and a little bit more messy, but you have seen these equations before. And before we move on, I do want to explain to you what a calorimeter is, and this would have been the calorimeter that we would have used for that hot Cheeto experiment. So a calorimeter is just a device that's used to measure the amount of heat involved in a chemical or physical process. So scientists use well-insulated calorimeters that all but prevent the transfer of heat between the calorimeter and its environment. So notice that this image, these are 2 coffee cups, and the reason why we use 2 coffee cups, it's because we don't want any of the heat that's inside to escape into the outside environment, or we also don't want any heat to come inside that environment or that inside liquid. In the laboratory, a coffee cup calorimeter is frequently used to determine the specific heat of a solid or to measure the energy of a solution phase reaction. So this is a very cheap calorimeter. There are calorimeters that cost thousands of dollars. We would have been using this one in class because I could easily purchase coffee cups, I have thermometers, and I have stirring rods. But yes, a calorimeter is just a device that helps us determine the amount of heat transfer in objects or chemical reactions. So please write this slide down, make sure that you have it in your journal before you move on to the next slide. Before we look at an example, I also need you to write down these 4 steps in solving a calorimetry problem. So step 1 is to identify your variables. So you will be identifying what the M is, what the Q is, what the specific heat is, and what the change in temperature is. The step number 2 is you're going to choose your equation. All of the problems that we will be seeing today involves 2 components, which means I have a hot object and a cold object. So we're going to be using the negative Q lost equals the Q gained. Step 3 is to just plug in with units, make sure that both sides have the same energy units. And step number 4 is to solve. So if you have not written these steps down, pause this video and write them down. This question: a quantity of 50 milliliters of water at 80 degrees, so I'm going to assume it's this first beaker, is added to 50 milliliters of water at 20 degrees Celsius. What would be the final temperature of that total volume? Notice that I have these 2 beakers with the same amount of water, 50 milliliters. So they're both the same amount of water. The biggest difference between these 2 beakers is the temperature. This one's hotter at 80 degrees Celsius. This one's colder at 20 degrees Celsius. It's a 2 component because I have a hot object and a cold object. So I'm going to identify my variables. Again, my volume, 50 milliliters is the same thing as 50 grams for water. And that's because water is very perfect. It has, for every 1 gram of water, I also have 1 milliliter. So it just works out perfectly. 50 milliliters is the same thing as 50 grams for only water. The initial temperature of this first beaker is 80 degrees. The initial temperature of this second beaker is 20 degrees. And I can identify that this first beaker is hotter and this cold beaker is colder. So I know that my heat will be transferring from the first beaker to the second beaker. And I'm going to choose my equation. Since this is a 2 component, I will be using the negative Q lost equals the Q gained. And I'm going to go on to a new slide with a third step. So make sure that you have these first 2 steps already written down. If not, just pause this video and then write these down, because I will be removing this whole slide out. The third step is to plug in with a unit. So we're going to be using that very complicated looking equation, but it's not complicated at all. So I know what my mass is, I know what my initial temperature is, and because it's water, I also know the specific heat. Remember that the specific heat of water, which is C, it's always going to be 4.184 joules per gram per degree Celsius. So that's a number that I asked you to memorize, because we will be using it quite frequently. So again, 50 grams, because that's what I figured out from that example. And this C, 4.184, this is just for water. Water will always have this specific heat, 4.184. I have the initial temperature, which is 80 and 20 degrees, but when I combine them, I'm going to have a final temperature, and both of those 2 objects will share that same temperature. So I'm going to denote the final temperature for both objects as X. And so it is your responsibility to manipulate this whole thing to isolate X and figure what X is equal to. You can plug this in a TI Inspire. If you have that software, you can numerically solve for X. If you don't have an Inspire, then you could go to Wolfram Alpha and do the same thing. But if you don't have any of those things, then you will be doing this by hand. Notice that it's very easy to simplify this. So I can multiply this 50 and this 4.184. And that's going to give me 209.2 on both sides, because I have the same mass for both beakers and it's the same type of substance. They have the same specific heat of 4.184. To further simplify this, I'm going to divide one side by 209.2. That should equal, that should make them equal to 1. So notice how this and this equal to 1, and I'm left with just X minus 20. And I have a 1 because 209.2 divided by 209.2 is the same thing as 1, but have a negative sign. You're going to distribute this negative sign to both of these variables. So you're going to have a negative X and a positive 80. And on the right hand side, you're still going to have the X minus 20. To simplify this even more, what I'm going to do is I'm going to add that X to both sides. Notice that this will cancel out this X, and I'm going to have a 2X on this side. I still have a minus 20 on the right hand side, but I finally got my 80 to be on the left hand side on its own. I think I need to add 20 to the right hand side so that it cancels out and I'll be left alone with a 2X. If I do that, then I'm going to add that 20 also to the left hand side, and that's going to give me 100 equals 2X. 100 equals 2X can be simplified to X equals 50. So 50 will be my final temperature. Second example. Pause this video, write this whole question down. This question is asking, how much will the temperature of a cup of coffee, which is 180 grams, starting at 95 degrees Celsius, be reduced when a 45 gram silver spoon, and I'm giving you the specific heat of the silver spoon, which is 0.24 joules per gram per degree Celsius, at 25 degrees Celsius, is placed in the coffee and the two are allowed to reach the same temperature. Assume that the coffee has the same density and specific heat as water. Okay, so I know what the specific heat of water is. Again, it's 4.184 joules per gram per degree Celsius, and that's the same specific heat that coffee will also have. So I'm going to identify my variables. My variable for coffee, I have 180 grams. My specific heat, just like water, is 4.184 joules per gram per degree Celsius. My initial temperature, this problem is stating that I start at 95 degrees Celsius. I don't know what my final temperature will be. That's something that I'm looking for. Let's do the same thing for the spoon variables. I know that the spoon is 45 grams. The specific heat is much lower than that of coffee. It has a 0.24 joules per gram per degree Celsius. The initial temperature is 25 degrees Celsius. When I put in my spoon in the coffee is going to release some of that energy into the spoon because the coffee is hotter than the spoon. So I'm going to have this type of heat transfer. Coffee is the hottest object, the spoon is the coldest. So the heat will be transferred from the coffee to the spoon. Okay. My second equation, because this is a two component problem, I'm going to have to use the negative Q lost equals the Q gain. The variables for the Q lost, that's going to be the hot object. So the 180, the 4.184, and the 95 degrees Celsius, that's going to go on the negative Q lost. These variables, the 45 grams, this specific heat, and the initial temperature of 25, that's going to go on the Q gained because it belongs to the spoon, which is the object that gained that energy. So make sure that you have all of this written down before I move on to the next slide. What I did here on this second step, I know that Q is the same thing as MCAT, so I just made it a little bit more longer, but we're going to have to use this bottom equation. And luckily we have all of these variables for the exception of the final temperature, and that's what we're going to figure out. So on the third step, you're just going to plug in on that negative MCAT equals positive MCAT. Remember that your mass of the coffee is 180 grams. You're going to multiply that by the specific heat of the coffee, which is 4.184 joules per gram per degree Celsius. You're going to multiply that by the change in temperature, but we don't know what the final is, so I'm going to label that final temperature as X. Keep in mind that all of this left-hand side has this negative sign. Okay, do not forget this negative sign. This sign is super important. On the right hand side, on the spoon side, I have 45 grams. I'm going to multiply that by 0.24 joules per gram per degree Celsius. I don't know what the final temperature is, but I know that it will be the same temperature as the coffee when they're both in equilibrium. But I do know that the spoon started at 25 degrees Celsius. In order for me to solve for X, I'm going to have to make this much simpler. And I could multiply these two values. So I should be getting 753.12 by multiplying 180 and 4.184. And if I multiply 45 and 0.24, I should be getting 10.8. I could simplify this even further. So why don't I divide these two sides by 10.8? This will ensure that I'm left with just x minus 25 on the right hand side. So if I divide 753.12 by 10.8, I should be getting 69.7. And notice how on my right hand side, I was able to isolate x minus 25. What you will be doing next is you're going to be distributing this negative 69.7 to these two variables. So you're going to have negative 69.7x my plus, because remember that this is a negative sign, so this negative sign will also be distributed to this negative 95, and that's going to give you positive 6,624.7. What you're going to do is you're going to try to get rid of this 69.7x by adding it on both sides. And if you do that, you're just going to be left with 6,624.7 on the left hand side, but you're going to have 70.7x on the right hand side. I'm going to try to get rid of this minus 25, bring it onto the other side by adding 25, and I should be getting 6,649.67 equals 70.7x. It's very easy to continue from here. You're just going to divide both sides by 70.7 to isolate x, and x should be equal to 94 degrees Celsius. Again, there's a lot of math in this, but if you just follow these same steps and you isolate that missing variable, you could use a four function basic calculator and you'll be okay. I was able to do this with my basic calculator. But if you don't want to struggle, then I suggest that you get yourself an Nspire software, or that you know how to use Wolfram Alpha, because literally you can just plug in all of this top thing. It looks very messy just the way that it is, and it will solve X for you without having to do all of this process. But if you don't have that, then you're gonna have to follow these steps. Third example. And the reason why I'm doing a third example, I know that I've been talking way too much, but I just need you to understand how to do these questions. So pause this video and make sure that you are writing this whole entire thing down. So a piece of an unknown metal weighing 59.047 grams was heated to 100 degrees Celsius and then put in a 100 milliliter of container of water, which initially had a temperature of 23.7 degrees Celsius. The metal and the water were allowed to come to an equilibrium temperature, determined to be 27.8. You're going to have to calculate the specific heat of that unknown metal. This is a little bit different from the two examples that we've done. For the other two examples, we have been trying to figure out what the final temperature of both objects at an equilibrium temperature. But this example is already giving you the equilibrium temperature, the final temperature of both objects. The only thing that you're going to have to solve is for the specific heat of the metal. And actually this example is a little bit easier because of that. First thing, identify your variables. You're going to identify the variables of your unknown metal. So this problem is telling me that I have 59.047 grams of this metal. I do not know what the specific heat is, so that's going to be denoted as X. The initial temperature starts at 100 degrees and the final temperature is 27.8 degrees Celsius. We're going to have to identify the variables for water. I also know that I have 100 grams of water. I know it says milliliters, but make sure that you understand that 100 milliliters of water is the same thing as 100 grams. The specific heat of water, although it doesn't give it to you in the problem, you should already know that the specific heat of water is 4.184 joules per gram per degree Celsius. The initial temperature of the water is 23.7 degrees Celsius, and the final temperature is 27.8 degrees Celsius. 27.8 degrees Celsius. The only thing that you're trying to figure out from these variables is the specific heat of this unknown metal, and since my unknown metal is the hottest object, I know that the heat will be transferred from this metal to the water. So all these variables are going to go on the left hand negative side of the Q. All these variables are going to go on the right hand side of the Q. My third step is to plug in with units. I know, again, it looks complicated, but this is much simpler. Remember that the Q lost, which is on the left hand side, that is my unknown metal variable, so this grams belongs to my metal. The change in temperature also belongs to my metal, and I'm trying to figure out what the specific heat of this metal. On the right hand side, I have all of the variables for water, because water was the object that was absorbing or gaining that heat from that hot metal. I have 100 grams of water. I'm going to multiply that by 4.184 joules per gram per degree Celsius, and I'm going to multiply it by the change in temperature. I could simplify this Let's do that. So 27.8 minus 100, that equals to negative 72.2. If I simplify these, the 27.8 minus 23.7, that equals to 4.1. I could further simplify this by multiplying whatever I can. So this 100 times 4.184 times 4.1. That's going to give me 1,715.44. I could also multiply the numbers that I have on the left hand side. So I can multiply 59.047 times negative 72.2. That's going to give me negative 4,263.1934 times x. Notice that I have a negative times a negative. You know what that means? They cancel each other out. It becomes a positive. So now I have positive 4,263.1934 times x. That equals 1,715.44. I could simplify this even further. I could isolate this x by dividing by 4263 on both sides. If I do that, then my x, which is also known as the specific heat of the water, that equals to 0.40 joules per gram per degree Celsius. That is actually it for this whole slide, for this entire PowerPoint. Please make sure that you go back and understand how to do these problems. A lot of it is just the math that could be tricky, but have a calculator handy when you do these problems. I have already created your quiz that is due on, whoops, not that. If you go to the Teams chemistry page and you go to assignments, then I haven't yet posted it, but I already have it already made. It's gonna come in the assigned quizzes. It's going to be called Calorimetry, and I'm going to give you a whole bunch of days to do this, just so that you could have time and figure this out on your own. So it's taking a bit, but it's already going to be up there by the time I release this video. Why is the internet not working? Anyway, please check on the assignments and complete this quiz. It's basically just 4 problems, but there are 8 questions. The thing is that some of those questions are they're part of the same problem. And my cat is bothering me again, and he's on the table. Can you stop it? Anyway. Yeah, it's not connecting, but it's up there. So please make sure that you do that. Thank you so much, guys. I've been talking way too much, but there's my video. That's my lesson. Please reach out to me if you have any questions. I will be providing more Melissa Marable videos regarding this concept. She's pretty cool, and she probably explains this way better than I do. So thank you so much for tuning in, and have a great day. Bye.